In our next example, we're going to look at a continuous distribution. In the first example, we had a discrete distribution. With a continuous distribution, we can do the same basic steps, though. So let's let the random variable x denote the amount of time a randomly selected person spends waiting in line at a grocery store. And so the claim is that x has an exponential distribution. Remember back when we talked about exponential distribution, we often used it to describe waiting time or time between events. So this seems like a reasonable claim. So we're going to use some data and the chi-squared goodness of fit test to test this claim. So if x has an exponential distribution, that means that its PDF is f of x equals lambda e to the negative lambda x, where lambda is some positive number. Now in this case, we're not making a claim about the value of lambda, and in fact we're going to have to estimate it from data, but this is the type of distribution that x has. At least that's what we're claiming. So in our data, we're going to go out and observe 30 values of x. Why do we do 30? Just because it's a nice round number. And so one person waited a total of 0.03 minutes, the next person waited a total of 0.04 minutes, and so on and so forth. So here's 30 observed values of x. Now, in order to use our distribution, we need to estimate the value of lambda, the parameter. Remember, in an exponential distribution, the mean was 1 over lambda, or stated another way, lambda is 1 over the mean. And so that means that lambda should be approximately 1 over the sample mean. So if we add up our 30 values, divide by 30, we get a sample mean of 1.41. We do this arithmetic, it comes out to be 0.71. So that means that the claimed PDF of x is approximately equal to this. So here we simply plugged in lambda equals 0.71. So there's our claimed PDF. Now the next step is to create a small frequency distribution of our data. And so here we're going to choose to use k equal 5 categories. Why did we choose 5? Well, just because it was a nice round number. But as we're going to see in a bit, that this number of categories was actually too many. So specifically what we mean by 5 categories is we're going to look at intervals from 0 to 1, 1 to 2, 2 to 3, 3 to 4, and then 4 to infinity. And so from our data, we have a total of 15 data values in this first interval, 8 in the second, and so on and so forth. Now let's let p sub 1 equal the actual probability that x is in this first interval. Or stated another way, this is the actual probability that x is between 0 and 1. Now, if x really did have this exponential distribution, with then the probability that x is in this interval would be, well, to calculate that, we simply need to integrate our density function over that interval 0 to 1. And so if we do that, we get a probability of about 0.5. So we're going to call this value pi sub 1. So this is the claimed probability that x is in this first interval, and this is the actual probability that x is in that interval. So we can calculate other values of pi in the same way. So this value right here is we integrate the density function from 1 to 2. This one we integrate from 2 to 3, integrate from 3 to 4, and then this one we integrate from 4 to infinity. So these are all the claimed values of those probabilities. Now, to get the expected values, we simply take our claimed probabilities times the total number of data values, which is 30. So here's the expected values. Here's our actual observed values. Now, if we note here that these expected values, these last 3 expected values, are all small. They're less than 5. And so one of our requirements for the goodness of fit test is that each of our expected frequencies was greater than 5. So we don't meet that requirement. And so to overcome that, we're going to combine these last 3 categories into just one big category. So in this so we're going to combine these into one category as the interval from 2 to infinity. And so if we do that, we're going to get this table here. So here's our three intervals, 0 to 1, 1 to 2, 2 to infinity. Here's the values of pi sub I. Again, these are calculated. This one is calculated by integrating the density function over this interval. Here we integrate from 1 to 2, and here we integrate from 2 to infinity. Here's the observed frequencies, and so this number 7 was found by adding up those last three observed frequencies. And then here's our expected frequencies. Again, those are calculated by taking the claimed probabilities times 30. And then here's the calculation of our test statistic, 0.0646. So very small number. This test statistic we can think of as a measure of the difference between these observed and expected values. If C is small, that means there's not a lot of difference between these values. We can see from the table that there's just not a lot of difference. If this test statistic is large, that would indicate that there's a lot of difference between the observed and the expected values. Now next we need to find our critical value, but notice that in our distribution, or to calculate the claim distribution, we needed to estimate the value of lambda. And so whenever we estimate the value of a parameter from data, we quote-unquote lose a degree of freedom. So what that means is that originally we had a number of categories minus 1 degrees of freedom. But now because we lose a degree of freedom, we have to subtract another 1. So we only have 1 degree of freedom here instead of 2. And so our critical value is chi-squared sub 0.05 with 1 degree of freedom. If we look that from our table, that comes out to be 3.841. And so now we come to our technical conclusion. We compare the critical value to, or the test statistic to the critical value. The test statistic is much smaller, and so we do not reject the null hypothesis. And again, the null hypothesis is the same as the original claim, and so we would conclude that it is reasonable to assume that the wait time is described by an exponential distribution.